Okay, we are going to look at chapter 15, which is about temperature and expansion. And so, what we're going to cover in here is temperature and heat expansion for the first part. So let's go look at temperature. So temperature is deceptive for many of us. Hot and cold are relative terms. Your body is not actually that good at telling temperature. So, for instance, right now, if you put one hand on your desk and one hand on a book, you'll probably say that the book is warmer than the table or the desk. That's not true. What's happening is that the desk is a conductor of heat energy. So your hand starts to lose energy and feels cold. And the book is an insulator. So it keeps your heat energy in your hand. But that doesn't mean the desk is colder. The desk is the same temperature as the book. They're both at room temperature. So, yes, so a lot of times our bodies are not that good at being able to tell what an actual temperature is. We just know whether or not we're losing heat energy. Actual temperature measured by a scientist is the average kinetic energy of the molecules of the substance. So, kinetic energy, the molecules are moving, they can be vibrating, they can be zooming along, um, moving fast, moving slowly. All that contributes to a kinetic energy. And because there are millions and millions of molecules, we don't just measure one, we consider the average kinetic energy. So that's what temperature for a scientist is. Now, we use thermometers to measure temperature. Thermometers usually have they have different materials that have different physical properties. So, for instance, if it was a mercury thermometer, the mercury would expand as it heated up, and that would make the level rise in the thermometer. But we have other physical properties that are used for thermometers also. We don't usually use expansion so much anymore. We use a lot of electrical devices and other properties. So, anyway, so thermal expansion is often still used for regular thermometers. So it can be the expansion or contraction of metal or the expansion and contraction of mercury or alcohol. But a lot of you are using a digital thermometer like this. And what that has to do is it's two little wires that are joined together, welded together of different materials. And it's called a thermocouple. And that thermocouple measures the temperature because the two different wires produce a voltage difference across them as temperatures change. Anyway, so the thermocouple is what we use a lot of times, and that's more of an electrical property. All right, so we use a lot of digital thermometers nowadays, but let's go back and look at the old kind, which you probably still have around your house. Often what's used is a bimetallic strip. So there's brass and iron welded together along their length, as you can see down here. What happens is that the brass expands more than the iron. And so when the strip is heated, it has to curve. So when it's heated up, the brass expands more than the iron, and that causes a curve in the coil, in the strip. And the opposite happens when it cools. When it cools down, the brass contracts more, and so it curves the other direction. So we can use this strip to tell temperature. Now, we usually use it as a coil. So in the back of a thermometer, if you've got a thermometer out on your outside on your deck or something, it probably has a coil in the back. Okay, and all that you have to do then is take, so the bimetallic strip is usually a coil. And what happens is as temperature increases, of course, the coil will extend. And if it decreases, the coil goes back. So what happens is that then you just attach a needle to that. So there's a needle, and so it goes back and forth with the strip, and then you just have to put some marks in, and you've got yourself a thermometer. So here's an old thermostat too. Thermostats in houses used to use bimetallic coils also. And so here's the coil, and what happens is as the temperature heats up, the coil expands, and that causes this little glass tube, which has some mercury inside. The mercury rolls around and makes contact with the wires over here, and that can turn on the air conditioning, or it can, turn off the furnace and do other things, because you're using the mercury, which is a metal, as a conductor of electricity. Anyway, actually, I've got one of these to show you. So here's a old-fashioned thermostat, and on the top, you can see that you have the switches that you would adjust, but now you can see inside. Let me take you above it. Okay, so inside you can see that there are these little glass tubes filled with the mercury. And so what would happen is when you were changing the setting on the switch, let me try to do that so my hand's not in the way. Okay. So as you change the setting on the switch, you would change which way the mercury would rock. So it would reach a certain temperature and the mercury would be in the right place as it expanded to make the contacts. And so this is a pretty fancy one. It's got 3 tubes of mercury so that you could turn the air conditioning on and off, turn the furnace on and off, and so on. Anyway, so that's what we used to have inside houses. But of course, the problem with mercury is it's a marvelous material, but it is dangerous. So mercury is an element that can cause brain damage. And you've probably heard the phrase the Mad Hatter, which you thought was just a funny phrase, maybe from Alice in Wonderland. But the thing is that hatters actually were known to be a little bit crazy. And the reason was that in those days, they would often be making those men's formal hats out of furs. Those furs had to be cured so that they didn't smell. And so what they would do is they would put mercury in with the furs. And so what would happen is that the mercury fumes would get to the hatters and they would go crazy when it reached their brain. So anyway, so they decided that maybe mercury wasn't the best thing to have in a house. So most of those have been replaced. If you have one hanging around your house, you don't know what to do with it, you can always donate it to the college, and we can use it as displays. But don't just throw it in the trash. You don't want mercury in the landfill. Anyway, so materials do expand and contract as they are heated and cooled. And one of the questions, though, is, you can see something like this sphere is obviously going to get larger as it expands. But what about this ring? The outside, you can imagine, is going to get larger. But what's going to happen to the hole? Is the hole going to get smaller, or is the hole itself going to get larger? Well, it turns out that surprisingly, the hole gets larger because this whole ring will expand, and that includes the hole. So what happens is that the material gets, the metal material is expanding out like this, and so the hole actually gets larger also. And So anyway, so yeah, people think that it might go inwards, but think about if you had a whole bunch of friends holding hands in a circle, and their hands were kind of just down at their sides, but then someone said, okay, now make your hands, stiff outwards. Well, everybody would step back, right? You wouldn't go inwards towards the center of the circle, you would step out. And so that's what's happening here, is that um, material, the molecules are getting further away from each other. So they're not going to cramp closer together in the center of the circle. Okay, now here is a bridge. And sometimes you may have driven across these funky finger things and said, oh, I hope those don't make me fall down. Anyway, what those are is they're expansion joints. And so the expansion joints allow the bridge to expand and contract as they go back and forth. And so what happens is that bridges will expand, asphalt, concrete, metal, all the stuff in a bridge will expand and contract. So the expansion joints allow the bridge to do that. Roads and things will expand a little bit too, but they are more fastened to the earth. But a bridge, which is flying above the earth, has more potential for expansion. So anyway, so bridges are actually set on these rockers. And so you can see how nasty looking this is. But yes, the bridge can actually rock back and forth. And you don't usually see this because it's hidden in a pillar. Okay, so the idea is that the bridge will expand during the summer, contract during the winter. And so right now you can see the fingers are actually pretty far apart. So that means the bridge has contracted. So this picture must actually be winter. Whereas this picture, you can see how the fingers are very close together now. This has got to be summer. Okay, now you do have some homework that concerns the thermal expansion. There's a formula which your book may have incorrectly. Some editions of the book were missing one of the parts of the formula. The formula says delta L, the change in the length, equals L, the original length, times alpha, the expansion coefficient, times delta T, which is the change in the temperature. And what some of the books were missing was the L, the original length. Well, you can't find out the change in the length unless you know the original length. So anyway, so make sure that if you've got a textbook that's missing the length, that you go ahead and correct that in your book. Yes, sometimes textbooks are wrong. Okay, so I'm sure the author wrote it correctly, but somewhere it got left out. Okay, so let's look at this. So you can see we have expansion coefficients, and these numbers are just saying how much the bridge expands for each degree, basically, of temperature change. And it's not very much, which is good. You don't want your bridge expanding too much. So different materials expand different rates. Lead, you can see, expands the most. Quartz expands the least. Pyrex, if you've used chemistry material, the thing is that they want it not to expand too much when it's heated or cooled. And so Pyrex is an improvement over regular glass, which has quite 3 times as much expansion. So anyway, different materials expand different amounts. Do you see two that have the same expansion coefficient? And you might see that iron and concrete have the same expansion coefficient. And that's important because what do we put inside concrete? We put iron rebar to reinforce it. If the iron had a higher expansion coefficient, like maybe copper or aluminum, then it would poke right out of the concrete. And so it is just very fortunate that these two cheaper materials also have the same expansion coefficient, because otherwise we would have trouble. We wouldn't maybe have a material that we could put inside concrete to make it stronger. Okay, so something that people have to think about. Even wood expands and contracts. Okay, so we're going to do a problem similar to the ones that you would have in your homework about an imaginary copper bridge that is 200 meters long up in the Himalayas, where the temperature range is -50 to 70 degrees Celsius. How much does the bridge expand from winter to summer? Okay, so the things that we need are we need the original length, and you can see that the original length is L, right? 200 meters is right there. And then we need our delta T, which is here, -50 to 70 degrees. And then we need our expansion coefficient, which depends on the material. Well, this is copper. So let's go get alpha for copper, and it's 17 times 10 to the -6. And that's just per degree Kelvin, but you can use degrees Celsius. Either way works. So I'm just going to put per degree Celsius. Okay, now it doesn't have a unit like a meter because you're going to get the meters from the length. Okay, all right, so, and we want to keep the length as the unit. That's our final unit. Okay, so let's put these numbers together. So our length is 200 meters. And then we have our alpha, 17 times 10 to the -6. And then we have our temperature range. And so the change in the temperature, -50 to 70 degrees Celsius. So if I take temperature delta T is T final minus T initial. So I'm going to put it in here as T final is 70 degrees minus the -50 degrees. Okay, so then that's going to give me 200 times 17 times 10 to the -6 times 70 minus a -50. That adds them together to make 120 degrees temperature range. Okay, so what I'm going to do is multiply all the real parts of the numbers and leave the 10 to the 6th the way it is for the moment. So I've got 200 times 120 times 17. And that's going to give me 4, 0, 8, 0, 0, 0. And that's times 10 to the -6. So to figure out my better looking answer, what I'm going to do is move the decimal point 6 times using my 10 to the -6. So I'm going to take my decimal point from here, and I'm going to move it 6 times. 1, 2, 3, 4, 5, 6. And now you can see this just comes out to be 0.408. And what units are left? Well, units, the degrees Celsius cancels the degrees Celsius, and all I'm left with is meters. That's what we want. This is the change in the length. So 0.408 meters. So that's pretty big, right? That means the bridge is going to expand 41 centimeters about, right? So that's going to be an expansion of about this much. So now you can see why you might need some sort of expansion joints. Usually bridges have several expansion joints along the way. Okay, and by the way, there is no copper bridge that long, of course. All right, that would be very large. Okay, so let's continue looking at temperature. So thermometers usually are calibrated to 2 reference points. And currently, usually, there are reference points of the ice point and the steam point. So the ice point is also what you might call the freezing point of water. And of course, you probably know that that is for Celsius. They put that at 100 degrees. Oops, at 0 degrees Celsius. Okay, and the steam point is the boiling point of water, and that you probably already know is 100 degrees Celsius. But that wasn't the first standardized thermometer. The first standardized thermometer is the Fahrenheit thermometer, and it was not calibrated to the ice point and the steam point. The Fahrenheit thermometer by Daniel Fahrenheit. This was a long time ago. He lived from 1686 to 1736. And what's amazing is that we in America still use his thermometer today because it is actually a really nice human temperature scale. So anyway, so we like it. You know, Kelvin has these crazy numbers like 300s and stuff, and so a lot of countries, of course, have gone for the Celsius one, but the Fahrenheit one was meant to be comfortable for humans. Daniel Fahrenheit, what he did was to get his lowest point, his 0 degrees, he felt that no one should have to deal with negative numbers. So he figured that he would go for the coldest day in Germany. So he'd take his thermometer out every day and check to see what the temperature was in Germany. And so the coldest day where the thermometer went down to the lowest point, that became his 0. And that's one reason here in the United States, we rarely go below 0 degrees Fahrenheit in the winter. Because, of course, for us, our ice point is at 32 degrees, right? So the freezing point of water for the Fahrenheit temperature is 32 degrees. Now, then he wanted to set his 100, and so he decided to set it to the temperature of blood. So this is why when you have a fever, you're going over 100. Well, that's because that's the way it was set up. Now, the problem is he didn't have a bucket of human blood to dip the thermometer in. Instead, he went to a butcher shop and got some bull's blood. So it's not perfectly 100 degrees, our body temperatures. Instead, supposedly the average is about 98.6. So he was very close. But yes, what he was trying to do was work with a very human scale. Nobody wants negative numbers, so he picked the coldest day, so nobody would hardly ever have to go below 0, he thought. And then our blood temperature. So anyway, so that was based on, that was how Fahrenheit did his thermometer. Now, then come along Celsius, which is also called the centigrade thermometer. And that was set up very scientifically by Mr. Celsius. And so he wanted something that scientists could repeat in various parts of the world without having to get out a bucket of blood. And nobody knew the coldest day in Germany anymore. So anyway, so what he would do is, so his was based on the steam point and the ice point. So 0 is the ice point and 100 degrees is the steam point. Okay, or boiling point, right? Boiling point, freezing point. All right. But then came Mr. Kelvin, and he was doing experiments with gases. And he noticed that he was plotting the volume or pressure of gases as he cooled them down. And so he kept doing different gases. And the thing is, he was putting in his data points, and they all started pointing towards the same point. Right? So all these data points were going in the same direction. So he figured out that there was this point, which was minus 273.15 degrees, and that was actually the absolute 0, because that was the point where these gases would have lost all their energy. So each gas would now be still. The molecules wouldn't be moving around. They would have lost all their kinetic energy. And so they all seem to have the same point where that would happen. So he decided that that must actually be true zero. So this became the new zero in Kelvin degrees. But he kept the same scale as centigrade. So since this was minus 273, then let me put that down here. Then centigrade became plus 273.15. And he kept the same scale, so boiling point of water 100 degrees on the centigrade scale became 373. So he kept 100 degrees between these. So that one is really useful for scientists because here the zero has more meaning than just based on water. It's based on the universal spot where all objects have lost their energy. That's the Kelvin. Okay, so the Kelvin scale, like I said, you just add on whatever your Celsius degrees are. So like if we want to go room temperature in Celsius is about 20 degrees. So we add that on to the 273. So if we were measuring this in Kelvin, it would be 293. Okay, and body temperature, we would add that on, and that would be 310 for body temperature in Kelvin. Okay, but usually people use Celsius in the medical field. Okay, all right, but physicists will use Kelvin because it works better in the equations. All right, so we won't usually use Kelvin. We will be using Celsius. If you need to convert, there are, of course, formulas, and which I'm not going to go over too much. So that's the way this works. Okay, so that's all I'm going to say, I guess, on temperature. And we're going to go to part 2.